You know, all around us, every single day, there are invisible dangers just floating in the air we breathe. I'm talking about everything from explosive leaks to toxic pollutants, threats that are completely silent and unseen. So how in the world do we protect ourselves? Well, we rely on a hidden world of technology, these tiny, unsung heroes that act as our invisible guardians. And today, we're going to pull back the curtain on what they are: gas sensors.
Okay, so here's our game plan. We'll start with a quick look at what these guardians actually do. Then we're going to meet three of the most important types: the semiconductor sensor, the electrochemical sensor, and the catalytic sensor. And to wrap it all up, we'll figure out how you choose the right one for the right job. Sound good? Let's dive in.
So how do you detect something you can't even see? I mean, that's the big question, right? The absolute genius of a gas sensor is that it doesn't try to see anything. Instead, it takes a chemical interaction, like a gas molecule literally touching a surface, and it converts that into an electrical signal that a machine can actually read. It's technology translating the language of chemistry into the language of electronics. Pretty cool. And trust me, these things are everywhere. They are the reason that carbon monoxide detector in your house can literally save your life. They're out there monitoring air quality in our cities, they're controlling the emissions in our cars, and they're even helping doctors with medical diagnoses just by analyzing your breath. They really are the silent sentinels of our modern world.
All right, first up, let's talk about one of the most common types out there: the metal oxide semiconductor sensor, or MOS sensor for short. I like to call them the resistance detectives. And that's because their entire method is built on a really clever principle. When a certain gas shows up, their electrical resistance changes. Simple as that.
And here's what one looks like. If you've ever tinkered with electronics, you've probably seen one of these on a circuit board. Now, that little mesh cap isn't just for looks. It's there to protect the super delicate sensing element inside while still letting all the gas molecules get in. This specific one, the MQ6, is designed to sniff out LPG, the kind of gas you'd find in a grill tank. Okay, so if we could just peek under that little cap, we'd find the heart of the whole operation. And this drawing shows it perfectly. You've got the sensing element itself, which is usually a little piece of metal oxide. You've got electrodes to measure the electricity, and this is the important part, a tiny integrated heater. And that heater is absolutely crucial, as you're about to see.
So how does it all come together? Well, it's kind of like a three-step dance. First, in perfectly clean air, oxygen molecules just land and stick to the sensor's surface. Think of them like little gatekeepers, grabbing onto free electrons and just holding them hostage. This creates a ton of electrical resistance, basically a traffic jam for electricity. But when our target gas comes along, it reacts with those oxygen gatekeepers and pulls them away. Suddenly, all those trapped electrons are free to move again, the traffic jam clears, and the resistance plummets. And that sudden drop is the signal that says, hey, the gas is here.
Now, this diagram is a great way to visualize that first step. So the surface here is something like tin oxide. The blue dots, that's our oxygen, and they're holding on to those little black dots, the free electrons. As long as oxygen is in charge, electricity just can't flow very easily at all. It's a roadblock. So what's the bottom line here? MOS sensors are super sensitive and they're cheap to make, which is exactly why they are so common. But remember that little heater we saw? Well, that means they're also pretty power hungry. They have to stay really hot. We're talking 200 to 400 degrees Celsius just to keep those chemical reactions firing. Okay, on to our next type of sensor. This one's pretty different. Meet the electrochemical sensor. I call this one the tiny chemical battery. Why? Because instead of changing its resistance, this sensor actually generates its own electrical current when it meets a specific gas. It's like a battery that only switches on when its fuel, the gas it's looking for, is present. And they kind of look the part, don't they? They often have this very clean, precise, almost medical-grade look to them. And that's because that's where they really shine. This one here is made for incredibly accurate oxygen measurement, the kind of precision you'd need in a hospital or some high-tech laboratory. Now, if we look inside, things get a little more complex. You see, it's not just one electrode. There are three of them: a sensing one, a reference one, and a counter electrode. And they're all sitting in this chemical bath called an electrolyte. It's this three-electrode system that gives the sensor its incredible accuracy and stability. The process is really elegant. First, the gas molecules seep through a special filter and hit that sensing electrode. When they do, a very specific chemical reaction happens. That reaction itself actually creates a flow of electrons, a tiny electric current. And here's the best part. The more gas there is, the bigger the reaction and the stronger the current. It's a direct measurement. This simplified diagram shows it perfectly.
The gas molecule shows up, a reaction kicks off at the sensing electrode, and boom, an electron is set free to travel over to the counter electrode. That flow, that's the current we measure. It's a direct conversion of chemistry into electricity. So what's the big takeaway? These sensors are the specialists. They're incredibly accurate and highly selective, which means they are fantastic at picking out one specific gas from a whole crowd of others. On top of that, they barely use any power and they work just fine at room temperature. That makes them perfect for things like detecting specific toxic gases or for sensitive medical equipment. And now for our third and final sensor type. And this one takes a totally different approach. This is the catalytic sensor, and I call it the combustion detector. Its one and only job is to find flammable gases, and it does it by, well, by burning them. But don't worry, it's a very, very tiny, very controlled, and very safe little fire. I mean, you can just look at this thing and tell it means business. It's built like a little tank, and you can even see the safety certifications right there on the label for use in explosive environments. You find these in places like mines or heavy industrial plants, where a flammable gas leak isn't just a problem, it's a critical danger. So what's the secret sauce here? It's a brilliant little system that uses two tiny beads. You've got a detector bead, which is coated in a special catalyst to encourage that little fire. And then you have a reference bead right next to it that's totally inert. It does nothing. They're both heated up, but only one is actually designed to react. So here's how it works. When a flammable gas comes in, it starts to burn on the surface of that special catalyst bead. This tiny combustion gives off extra heat, which makes the detector bead hotter than its inactive partner, the reference bead. This difference in temperature causes a change in the detector bead's electrical resistance, and by comparing the two beads, the sensor can figure out exactly how much flammable gas is in the air. The most important thing to know about this sensor is that it is rock-solid reliable for detecting things that can go boom. It's fast, it's effective, but it does have one catch. It needs oxygen to work. I mean, it makes sense, right? You can't have a fire without oxygen. So there you have it. We've met our three invisible guardians: the resistance detective, the tiny chemical battery, and the combustion detector. And as you can see, each one is a specialist, which leads to the big question: which one do you call when you need the job done?
This table really just lays it all out. Your semiconductor sensor is your low-cost, highly sensitive generalist, but it's a real power hog. The electrochemical sensor is your precise, low-power specialist, but it has a limited lifespan, so you'll have to replace it eventually. And the catalytic sensor is your ultra-reliable safety expert for flammable gases, but it's useless without oxygen.
Ultimately, it all boils down to this one simple idea. You need different sensors for different dangers. Choosing the right technology is all about understanding the specific threat you're trying to find and the environment you're in. There is no one-size-fits-all solution here. Which really leaves us with a final thought to chew on. We rely on these amazing devices to detect the dangers we know about today: the carbon monoxide in our homes, the methane in our mines. But as our world keeps changing and as we demand more and more data about the very air we breathe, what new invisible threats will the next generation of sensors need to find? That's something to think about.